Now we're just starting to really explore the last frontier, which is the ocean, at the same time that we need it.
Cutting-edge technology is enabling a new generation of aquanauts to explore deeper than ever before.
Imagine an environment covering over 70% of our planet, yet less explored than the surface of the moon. The deep sea, a realm plunged into perpetual darkness and subjected to crushing pressures, remains Earth's final frontier.
The race is on to the final frontier. The deep.
It's a place so vast and alien, it challenges our very understanding of life and physics. Down there, sunlight never penetrates, temperatures plummet, and the weight of miles of water bears down relentlessly.
If you think for a moment that everything's been found, that there's nothing left to do, here's a place where it hasn't happened. Roger that.
Yet somehow life persists in forms bizarre and wonderful. But beyond the known marvels lie profound, unsettling mysteries, enigmas that continue to baffle the brightest minds and hint that the strangest secrets of our world are still hidden, waiting in the abyss. The sheer scale of the unknown is staggering. What truly lurks beneath the waves far beyond our everyday comprehension?
They are opening up a whole new world of potential benefits to humanity. The risks are great, but the rewards could be greater. From a vast wealth of resources to clues about the origins of life.
It's a question that echoes with possibilities, some awe-inspiring, others deeply unnerving. We begin our dive into these bewildering depths by considering a sound, a single powerful noise that rippled across the entire Pacific Ocean, sparking theories of colossal, unknown entities and reminding us just how little we grasp about the forces at play in the deep. It serves as a stark auditory symbol of the ocean's immense and often inexplicable power. The bloop, an ocean-wide mystery sound. In the summer of 1997, something truly strange happened beneath the waves. Hydrophones, essentially underwater microphones, strategically placed thousands of miles apart across the Pacific Ocean by the U.S. National Oceanic and Atmospheric Administration, NOAA, picked up an extraordinary sound. It wasn't just any noise, it was an ultra-low frequency, yet extremely powerful, upsweeping sound, lasting for about a minute. Its origin was pinpointed to a remote region off the southwestern coast of South America. The sheer amplitude was astonishing. It was detected by sensors over 5,000 kilometers, 3,000 miles apart. Scientists nicknamed it the bloop. What could possibly create such a colossal noise, audible across an entire ocean basin? The characteristics of the sound didn't match known man-made sources like submarines or bombs, nor did they perfectly align with familiar geological events like earthquakes or volcanic eruptions. The frequency profile bore a resemblance to sounds made by living organisms, but the sheer volume was the baffling part. To generate a sound that could travel such immense distances through water, the source would have to be enormous, far larger than any known animal on Earth, including the blue whale, the planet's largest creature. This immediately fueled intense speculation both within the scientific community and among the public. Could it be a monstrous, undiscovered sea creature lurking in the unexplored depths? The idea was both terrifying and fascinating, tapping into ancient myths of krakens and sea serpents, life in the Mariana Trench. Beyond comprehension. Venturing into the Mariana Trench is like descending into another world, one operating under rules that seem utterly alien to surface dwellers. Located in the western Pacific, this crescent-shaped scar in the Earth's crust plunges down nearly 11,000 meters, almost 7 miles, at its deepest point, Challenger Deep. Imagine the pressure here, it's over 1,000 times the standard atmospheric pressure at sea level, equivalent to having 50 jumbo jets stacked on top of you. Sunlight is a forgotten memory, the darkness is absolute, eternal, and the temperature hovers just above freezing. It's an environment so extreme that for a long time, scientists questioned whether any complex life could possibly survive, let alone thrive, under such forbidding conditions. Yet expeditions using remotely operated vehicles, ROVs, and specialized landers have shattered these assumptions, revealing a surprisingly active ecosystem. Instead of a barren wasteland, researchers found life, strange, resilient life adapted in ways we are only beginning to understand. Among the most fascinating discoveries are the xenophyophores. These are giant single-celled organisms, amoeba-like protists that can grow up to 10 centimeters, 4 inches, across, constructing intricate shells from minerals and sediment particles. They are masters of surviving the crush, somehow maintaining their delicate structures. Alongside them, scuttle amphipods, crustacean relatives resembling shrimp, some surprisingly large, feeding on the scarce organic matter that drifts down from above like marine snow. Bacteria also abound, forming mats on the seafloor and underpinning this unique food web. The elusive giant squid behavior unknown. For centuries, the giant squid, Architeuthis ducks, existed largely in the realm of myth and legend. Tales of krakens, monstrous tentacled beasts capable of dragging ships to their doom, filled maritime folklore. For a long time, the only physical evidence came from carcasses washed ashore, often damaged and decomposed, or from the sucker scars found on the skin of sperm whales, their known predators. These tantalizing fragments hinted at a creature of immense size and power dwelling in the inaccessible depths, but its true nature remained elusive. Seeing one alive in its natural habitat was the holy grail of marine biology, a challenge that spanned generations of researchers. The breakthrough finally came in 2004 when Japanese scientists captured the first images of a giant squid in the deep ocean, followed by the first filming of an adult in its natural environment in 2012. These encounters were monumental, confirming the existence of these giants beyond doubt and providing invaluable glimpses into their world. We learned they possess the largest eyes of any known animal, likely adapted for spotting faint bioluminescence in the dark. We saw their powerful tentacles and fins. However, these fleeting moments, while groundbreaking, have only scratched the surface of understanding this incredible animal. Many fundamental questions remain unanswered. How do they actually behave on a daily basis in the crushing darkness? What are their primary hunting strategies? Are they ambush predators, or do they actively pursue prey? Their interactions with sperm whales are known from scars and stomach contents, but how often do these titanic battles occur? And what are the squid's defensive tactics? Anglerfish mating, a parasitic nightmare. The deep sea is home to creatures that look like they swam straight out of a nightmare, and the anglerfish, with its gaping maw, needle-sharp teeth, and bioluminescent lure dangling temptingly in the darkness, certainly fits the bill. These predators are masters of the ambush, using their light organ packed with glowing bacteria to attract unsuspecting prey in the pitch-black abyss. But perhaps the most astonishing and frankly unsettling aspect of anglerfish biology isn't their hunting technique, but their profoundly bizarre method of reproduction, a process involving extreme sexual dimorphism and permanent parasitic attachment. It's a strategy so strange it defies easy explanation. In many deep-sea anglerfish species, the difference between males and females is staggering. The female is the large, fearsome predator we typically imagine. The male, in stark contrast, is tiny, often minuscule compared to his mate, and underdeveloped in many ways except for one, his sense of smell. His primary purpose in life seems to be solely to find a female. Once he detects the specific pheromones released by a female of his species in the vast, dark ocean, he hones in on her. Upon finding her, his quest takes a truly macabre turn. He bites onto her body, often on her belly or flank, and latches on firmly. Hydrothermal vents, cradles of strange life. Imagine exploring the deep ocean floor, thousands of meters down in perpetual darkness, and suddenly encountering towering chimneys spewing superheated, mineral-rich water that looks like black smoke. This was the astonishing sight that greeted scientists in 1977 near the Galapagos Rift, leading to the discovery of hydrothermal vents, geological phenomena that completely revolutionized our understanding of where and how life can exist on Earth. These black smokers and their cooler cousins, white smokers, are essentially underwater hot springs, formed where seawater seeps into the ocean crust near volcanically active areas, gets heated by magma, dissolves minerals from the surrounding rock, and then bursts back out onto the seafloor. What truly stunned researchers was not just the vents themselves, but the teeming ecosystems clustered around them. In a realm utterly devoid of sunlight, where photosynthesis is impossible, life was thriving. Instead of relying on the sun's energy, these unique communities are based on chemosynthesis. Specialized bacteria and archaea form the base of the food web, harnessing chemical energy from the sulfides, like hydrogen sulfide, toxic to most life, dissolved in the vent fluid. These microbes oxidize these chemicals to produce energy, much like plants use sunlight. This microbial life supports an incredible array of bizarre creatures found nowhere else on Earth. Giant tube worms, Riftia pachyptila, up to 2 meters long, lacking mouths or digestive systems, relying entirely on symbiotic bacteria packed within their bodies. Dense colonies of vent mussels and clams also harboring chemosynthetic symbionts. Strange crabs, shrimp, and fish adapted to the hot, toxic, high-pressure environment. Cold seep communities, methane-fueled existence. While hydrothermal vents are dramatic hotspots fueled by volcanic heat, the deep ocean floor hosts another, quieter type of chemosynthetic ecosystem, cold seeps. As the name suggests, these areas are not driven by high temperatures. Instead, they occur where energy-rich fluids, primarily methane and hydrogen sulfide, slowly percolate or seep up from underlying sediments into the overlying seawater at ambient deep-sea temperatures, which are typically near freezing. These seeps can be found along continental margins and in subduction zones, often associated with underlying oil and gas deposits or methane hydrates, ice-like structures trapping methane. Like hydrothermal vents, cold seeps support unique communities of life that rely on chemosynthesis rather than photosynthesis. Specialized microbes, again bacteria and archaea, form the foundation of these ecosystems. Some microbes consume the methane seeping from the floor, while others utilize the hydrogen sulfide, which is often produced as a byproduct of methane consumption or anaerobic processes within the sediments. These microbial mats can cover large areas of the seafloor, sometimes associated with carbonate rock formations that precipitate as a result of the microbial activity altering the local water chemistry over long periods. These ecosystems, while sharing the principle of chemosynthesis with vents, present a contrasting picture. Life here tends to be much slower growing and longer lived compared to the often ephemeral and dynamic vent communities. Bioluminescence, the language of light. Step away from the concentrated oases of vents and seeps into the vast midwater, the pelagic zone, and you enter a realm where darkness reigns supreme. Yet this darkness is punctuated by fleeting, often spectacular displays of living light, bioluminescence. This phenomenon, the production and emission of light by a living organism, is remarkably common in the deep sea. Estimates suggest that up to 90% of deep-sea creatures possess this ability in some form. It's far more prevalent here than in any other environment on Earth, transforming the abyss into a dynamic theater of silent, luminous signals. Fish, squid, jellyfish, crustaceans, bacteria, and even some sharks utilize chemical reactions typically involving a light-emitting pigment called luciferin and an enzyme called luciferase to generate cold light in an astonishing array of colors and patterns. The functions of this living light are incredibly diverse, reflecting the intense selective pressures of an environment without ambient sunlight. For many predators like the anglerfish or the dragonfish, bioluminescence serves as a lure, dangling a tempting light organ to attract unsuspecting prey towards deadly jaws. Conversely, some prey species use flashes of light defensively. A sudden burst can startle or temporarily blind an attacker, allowing for escape. Others, like certain shrimp or squid, can eject clouds of luminous fluid, creating a confusing smokescreen while they make a getaway. Counter-illumination is another ingenious strategy. Some fish have light organs on their undersides that match the faint downwelling light from the surface, if any exists at their depth, effectively erasing their silhouette and making them invisible to predators looking up from below. Deep-sea gigantism. Why so large? While many deep-sea creatures are small or microscopic, the abyss is also home to startling examples of gigantism, where certain species grow significantly larger than their shallow water or terrestrial relatives. This phenomenon, known as deep-sea gigantism or abyssal gigantism, is one of the ocean's most intriguing biological puzzles. It's not universal, not everything down there is huge, but the exceptions are truly remarkable and demand explanation. Think of the giant isopod Bathanomus giganteus, a scavenger related to common woodlice, which can grow up to 50 centimeters, 20 inches long, dwarfing its land-based cousins. Consider the Japanese spider crab Macrochera caemphori, whose leg span can reach an astonishing 3.7 meters, 12 feet, making it the largest known arthropod. Other examples include giant sea spiders, pycnogonids, enormous amphipods found in trenches, and potentially the colossal squid, arguably the largest invertebrate by mass. Why do some deep-sea animals attain such enormous proportions? Scientists have proposed several hypotheses, but no single theory seems to fully explain the phenomenon across all affected species, suggesting a combination of factors might be at play. One prominent idea relates to the extremely cold temperatures of the deep sea. Cold water slows down metabolic rates and increases cell size and lifespan, potentially allowing animals to grow larger over longer periods before reaching sexual maturity, Bergman's rule applied to invertebrates. Another factor could be the immense pressure. While seemingly counterintuitive, some physiological models suggest that increased pressure might favor larger cell sizes, although the exact mechanisms are unclear. Unidentified deep-sea sounds beyond the bloop. The bloop may be the most famous, mysterious sound recorded in the deep ocean, but it's far from the only one that has left scientists scratching their heads. NOAA's network of autonomous hydrophones, originally deployed to monitor underwater seismic activity and clandestine nuclear tests during the Cold War, has inadvertently become an archive of unexplained acoustic events originating from the abyss. Over the years, several distinct, powerful, and unidentified sounds have been captured, each with its own unique sonic signature, adding to the library of deep-sea enigmas. These sounds fuel ongoing debate about their potential sources. Are they biological, geological, or perhaps even artificial in origin? One such sound is Slow Down. Recorded on May 19, 1997, the same year as the bloop, this sound also originated in the equatorial Pacific Ocean. Its name comes from its characteristic decrease in frequency over its duration, lasting about 7 minutes. Like the bloop, it was detected by multiple sensors across a vast distance. While initially suspected to be related to Antarctic ice activity, its location near the equator and specific acoustic properties make this explanation less certain for some researchers, leaving its precise origin open to speculation, potentially pointing towards large-scale geophysical phenomena or even unknown biological sources. The Baltic Sea anomaly, structure, or stone. Not all deep-sea mysteries involve strange sounds or bizarre creatures. Sometimes it's the shape of the seafloor itself that sparks intrigue and controversy. One of the most discussed examples in recent years is the Baltic Sea anomaly. In June 2011, a Swedish commercial treasure hunting team called Ocean X, led by Peter Lindberg and Dennis Osberg, was using side-scan sonar to search for old shipwrecks in the Bothnian Sea, a northern part of the Baltic Sea between Sweden and Finland. While surveying a particular area at a depth of about 85 to 90 meters, around 280 to 300 feet, their sonar detected something highly unusual, a large, roughly circular object approximately 60 meters, 200 feet in diameter, with seemingly geometric features including straight lines, right angles, and what appeared to be steps or ramps leading up to it. The initial sonar images were striking, showing an object that looked distinctly artificial, almost like a crashed flying saucer resting on the seabed, complete with what some interpreted as drag marks stretching behind it for hundreds of meters. This discovery quickly captured public imagination, fueled by speculation about its potential origins. Was it a previously unknown geological formation, a sunken man-made object from World War II, or something far more exotic? The Ocean X team reported further strangeness during subsequent dive expeditions to the site. They claimed that electrical equipment, including satellite phones and cameras, malfunctioned or stopped working entirely when their vessel was directly above the anomaly, only to function normally again once they moved away. Samples retrieved from the object were initially reported to contain unusual metals, though later analyses suggested mostly common rocks like granite, gneiss, and basalt, albeit with some burn marks reported on samples taken directly from the anomaly. The Yonaguni Monument, nature's trick, or ancient ruin. Off the southern coast of Yonaguni Island, the westernmost inhabited island of Japan, lies another underwater enigma that blurs the line between geology and archaeology. The Yonaguni Monument, sometimes referred to as the Yonaguni Submarine Ruins. Discovered in the mid-1980s by a local diver, Kihachiro Aratake, while scouting for new hammerhead shark-watching spots, this massive underwater rock formation features remarkably flat, parallel surfaces, sharp edges, apparent right angles, and structures resembling terraces, steps, pillars, and even a triangular shape likened to a turtle. The main structure is immense, roughly 150 meters, 500 feet long, 40 meters, 130 feet wide, and 27 meters, 90 feet high, resting at depths ranging from 5 to 30 meters, 16 to 100 feet. The appearance of these features immediately sparked debate. Is this a natural geological phenomenon, or is it evidence of a sophisticated, man-made structure submerged by rising sea levels millennia ago? Proponents of the artificial origin theory, most notably Masaki Kimura, a marine geologist from the University of the Ryukyus, argue that the concentration of seemingly carved features in one location is highly unlikely to be purely natural. They point to the symmetry, the precision of the angles, some appearing close to 90 degrees, and distinct formations they interpret as roads, walls, and possibly even a stadium or castle platform. If man-made, it would imply the existence of an unknown advanced civilization during the last ice age, when sea levels were significantly lower, potentially dating the structure back 8,000 to 12,000 years. This would dramatically rewrite human history in the region. Lost submarines vanished without trace. The deep ocean is not only a repository of ancient mysteries, but also the site of modern tragedies shrouded in uncertainty. The disappearance of submarines represents a particularly chilling category of maritime mystery. These vessels, designed to operate stealthily beneath the waves, can vanish suddenly and completely, leaving behind grieving families, bewildered navies, and enduring questions about their final moments. Despite sophisticated technology and often intensive search efforts, finding a sunken submarine in the vast deep ocean can be incredibly difficult, and determining the exact cause of its loss even harder. One prominent example is the USS Scorpion SSN 589, a skipjack-class nuclear submarine that disappeared in the Atlantic Ocean in May 1968. The submarine, with 99 crewmen aboard, was returning to Norfolk, Virginia from a deployment in the Mediterranean. Its last reported position was southwest of the Azores. When it failed to arrive on schedule, a massive search was launched. The wreckage was eventually found 5 months later, resting on the seabed at a depth of over 3,000 meters, 10,000 feet, hundreds of miles from its last known position. While the US Navy conducted extensive investigations, the exact cause of the Scorpion's loss remains officially undetermined and subject to speculation. Theories have ranged from a torpedo malfunction, a hot-run torpedo accidentally arming and exploding, a catastrophic mechanical failure, a battery explosion, or even, though less likely, hostile action during the Cold War. The secrecy surrounding nuclear submarines and the fragmented nature of the wreckage have prevented a definitive conclusion, leaving the fate of the Scorpion a lingering Cold War enigma. The Goblin Shark's alien jaw. Among the cast of strange characters inhabiting the deep sea, the Goblin Shark, Mitsukurina Ostoni, stands out for its distinctly unsettling appearance and a truly unique feeding mechanism that seems borrowed from science fiction. Often called a living fossil, this rarely seen shark belongs to a lineage dating back some 125 million years, retaining primitive characteristics that make it look quite different from more familiar sharks. It possesses a long, flattened snout, the rostrum, studded with sensory organs called ampullae of Lorenzini, used to detect the faint electrical fields produced by prey in the dark. Its skin is a flabby pinkish gray and its eyes are small, suggesting it relies more on other senses than sight in its deep water habitat, typically found near continental slopes and seamounts at depths below 100 meters. 330 feet, down to potentially 1,300 meters, 4,300 feet. What truly sets the goblin shark apart, however, is its incredible jaw. Unlike other sharks, its jaws are highly protrusible, capable of shooting forward dramatically and rapidly to snatch prey. When a fish, squid, or crustacean comes within range, the shark's ligaments holding the jaw relax and specialized muscles contract, causing the entire jaw structure, lined with slender needle-like teeth, perfect for grasping slippery prey, to catapult forward, extending almost to the end of its long snout. This slingshot feeding or slingshot jaw mechanism happens incredibly fast, allowing the shark to ambush prey effectively despite not being a particularly fast swimmer itself. The visual effect is startling, transforming the shark's seemingly placid profile into a terrifyingly efficient prey capture device in an instant. The rarely seen frilled shark. If the goblin shark looks like an alien, the frilled shark, Chlamydocelicus anguineus, resembles something dredged up from a prehistoric nightmare, a creature that seems to blur the lines between shark and sea serpent. Another living fossil, this species boasts a lineage stretching back possibly 80 million years, retaining numerous primitive features that set it apart from most modern sharks. Its body is long, slender, and eel-like or serpentine, reaching lengths of up to 2 meters, 6.6 feet. Its common name comes from the 6 pairs of frilly gill slits that extend around its throat, giving it a somewhat ruffled appearance. Its terminal mouth at the very front of its head, unlike the underslung mouths of most sharks, is lined with rows of distinctive 3-pronged, needle-sharp teeth, perfect for snagging soft-bodied prey like squid. The frilled shark inhabits the outer continental shelves and upper continental slopes, typically found at depths between 50 and 1,500 meters, 160 to 4,900 feet, although occasionally encountered shallower or deeper. Its distribution is wide but patchy across the Atlantic and Pacific Oceans. Despite this broad range, live sightings or captures are remarkably rare. Most of what we know about this species comes from specimens accidentally caught as bycatch in deep-water fisheries. Consequently, huge gaps remain in our understanding of its life history and behavior in its natural deep-water habitat. How does it hunt? Does its serpentine body allow it to strike like a snake, lunging forward to engulf prey, or does it use some other strategy in the darkness? Its diet seems to consist mainly of cephalopods, squid and octopus, other sharks, and bony fish, but the specifics are limited. Megalodon, lingering questions. The very name, Otodus megalodon, conjures images of unparalleled predatory power, a colossal shark that dominated the world's oceans for millions of years before vanishing relatively recently in geological terms. Existing roughly from 23 to 3.6 million years ago, Megalodon was undoubtedly one of the largest and most formidable predators ever to have lived. Our primary evidence for its existence comes from its massive fossilized teeth, which can be larger than a human hand, and occasional fossil vertebrae. These remains paint a picture of an apex predator likely feeding on whales and other large marine mammals. While its existence is undisputed fact, moving beyond the basic knowledge gleaned from teeth reveals a surprising number of lingering questions and mysteries surrounding this iconic prehistoric giant. One major unknown is Megalodon's exact appearance. While often depicted as a supersized great white shark, this is largely speculative. Fossil evidence suggests it belonged to a different lineage, the Otodontidae family, now extinct, and may have had a different body shape, perhaps stockier, with a blunter nose or different fin proportions. Reconstructions are based on extrapolations from tooth and vertebral centrum size, often using the great white as an analog, but its true form remains uncertain without more complete fossil skeletons, which are incredibly rare for cartilaginous fish like sharks. Similarly, its true maximum size is still debated. While estimates commonly range up to 15 to 18 meters, 50 to 60 feet, some analyses suggest potentially even larger individuals, perhaps exceeding 20 meters, 66 feet, though reaching consensus on these upper limits is difficult based on fragmented evidence. The scale of the unknown, undiscovered species. While we marvel at the known wonders and baffling mysteries of the deep sea, from bizarre creatures and strange sounds to colossal extinct predators, perhaps the most profound mystery of all is simply the sheer scale of what we don't know. The deep ocean, encompassing the vast volume of water below the sunlit zone, roughly below 200 meters or 650 feet, represents the largest habitat on Earth by far, yet it remains astonishingly unexplored. Estimates consistently suggest that a huge percentage of the species living in the deep sea have yet to be discovered, let alone described or understood. Some scientists estimate that potentially over 80%, perhaps even exceeding 90% of marine species residing in these dark, cold, high-pressure environments remain completely unknown to science. Think about that for a moment. The majority of life in the largest living space on our planet is still hidden from us. Every expedition using remotely operated vehicles, ROVs, autonomous underwater vehicles, AUVs, or deep-sea landers frequently encounters organisms that appear new to science. These range from microbes with unique metabolic pathways to new species of fish, corals, crustaceans, mollusks, jellyfish, and worms, often displaying adaptations as strange and wonderful as anything previously documented. The challenges of exploration are immense. The crushing pressure requires incredibly robust and expensive equipment. The vast distances and depths limit survey areas. The darkness makes visual observation difficult, and many deep-sea creatures are fragile and difficult to collect or study alive. We have mapped the surface of Mars with greater resolution than we have mapped our own deep ocean floor. Unpredictable deep ocean currents. Beyond the biological mysteries, the physical environment of the deep sea itself presents profound and complex puzzles, particularly concerning the movement of water masses. We often think of the ocean's depths as static and unchanging, but this couldn't be further from the truth. Vast, slow-moving currents circulate through the abyss, driven by differences in water temperature, thermo, and salinity, haline, a process known as thermohaline circulation, often conceptualized as the global ocean conveyor belt. This massive system plays a critical role in distributing heat around the planet, influencing global climate patterns and transporting nutrients and dissolved gases like oxygen and carbon dioxide into the deep ocean. However, predicting and fully understanding the behavior of these deep currents is incredibly challenging. While the general pattern of the conveyor belt is known, typically involving cold, dense water sinking at high latitudes like the North Atlantic and near Antarctica, flowing slowly along the ocean floor towards the equator, gradually warming and rising, and eventually returning towards the poles as surface currents. The details are far more complex and dynamic than this simplified model suggests. Deep ocean currents are influenced by seafloor topography, mountains, ridges, canyons, geothermal heating from the Earth's interior, wind patterns at the surface affecting water mass formation, and mixing processes that are still not fully quantified. Measuring these slow, deep flows directly requires sophisticated instruments deployed for long periods, making comprehensive mapping difficult. Seamounts, biodiversity hotspots. Rising like underwater islands from the abyssal plains, seamounts are mountains that do not breach the ocean's surface. There are estimated to be tens of thousands, perhaps even over 100,000 of these submerged volcanic peaks scattered throughout the world's oceans, making them one of the most common geological features on the planet. Despite their prevalence, the vast majority remain unexplored and unmapped in detail. What makes seamounts particularly fascinating and somewhat mysterious is their tendency to be biological hotspots, harboring incredibly rich and often unique ecosystems compared to the surrounding deep-sea floor. They are oases of life in the generally food-poor abyss. Why are seamounts so productive? The answer lies in the complex interaction between their physical structure and ocean currents. As deep currents flow across the ocean basin, they encounter the obstruction posed by a seamount. This forces water to flow up and around the slopes, creating localized upwelling and turbulent mixing. This process can lift nutrient-rich deeper water closer to the upper layers, though still often below the sunlit zone, and trap plankton and organic particles carried by the currents. This enhanced food supply attracts and supports dense communities of suspension feeders, particularly deep-sea corals, like stony corals, black corals, and gorgonians, and sponges. These organisms in turn create complex three-dimensional structures that provide habitat, shelter, and feeding grounds for a diverse array of other species, including crustaceans, mollusks, echinoderms like sea stars and brittle stars, and a variety of fish. The journey of marine snow. Life in the vast majority of the deep sea, away from the localized chemical energy sources of vents and seeps, relies heavily on a constant, gentle drizzle of organic material falling from the sunlit waters above. This continuous shower of detritus is known as marine snow. It's composed of a wide variety of particles: dead plankton, phytoplankton, and zooplankton, fecal pellets from small animals, discarded mucus structures like larvacean houses, shed exoskeletons, dust, and other organic debris. As these particles sink, they often clump together, forming larger aggregates that drift slowly downwards through the water column, resembling snowflakes in the beam of an underwater vehicle's light, hence the name. Marine snow is the primary food source for many deep-sea organisms, particularly those living in the water column, pelagic, and on the abyssal plains far from shore. Filter feeders capture it directly from the water, while deposit feeders consume the accumulated snow that settles on the seabed. This vertical transport of organic matter is a crucial link between the productive surface ocean and the energy-starved deep sea, effectively fueling the deep-sea food web and playing a vital role in the ocean's biological carbon pump. The process by which carbon fixed by photosynthesis at the surface is transported to the deep ocean, potentially sequestering it for long periods. Brine pools, lakes under the sea. Imagine descending to the crushing depths of the ocean floor thousands of meters below the surface only to encounter what appears to be a lake, a distinct body of water sitting within the surrounding seawater, complete with its own shoreline and sometimes even visible ripples on its surface. These surreal underwater lakes are known as brine pools, and they represent some of the most extreme and bizarre environments found on Earth. They form in areas where highly saline water, significantly saltier and therefore denser than normal seawater, emerges from underlying salt deposits, evaporates, buried beneath the seafloor sediments, or is created through other geological processes. Because this brine is so dense, it doesn't easily mix with the overlying ocean water, instead pooling in seafloor depressions. The chemistry of these brine pools is often radically different from the surrounding ocean. Besides being hypersaline, sometimes 3 to 8 times saltier than seawater, they are typically anoxic, meaning they contain virtually no dissolved oxygen. They can also be rich in dissolved methane, hydrogen sulfide, and other chemicals toxic to most marine life. The sharp interface between the dense brine and the normal seawater creates a visible boundary, often looking like an underwater shoreline. Any unfortunate fish or other organism that swims or sinks into the brine pool quickly succumbs to the combined effects of salinity shock and anoxia, its body often preserved for long periods due to the lack of oxygen and microbial decay within the pool itself, leading some to call them jacuzzis of despair. The vampire squid's ancient lineage. Neither a true squid nor a true octopus, the vampire squid, a Vampiroteuthis infernalis, literally vampire squid from hell, occupies a unique evolutionary position all its own, the sole surviving member of its own taxonomic order, Vampiromorphida. This enigmatic creature inhabits the deep, dark oxygen minimum zones, OMZs, of the tropical and temperate oceans worldwide, typically at depths between 600 and 1,200 meters, 2,000 to 4,000 feet, where oxygen levels are incredibly low, conditions lethal for most complex animals. Its appearance is as unique as its lineage. It has a gelatinous black or reddish body, large globular eyes, proportionally the largest of any animal, and 8 webbed arms connected by a cloak-like membrane. Unlike squids, it lacks feeding tentacles but possesses 2 long, retractable sensory filaments that can extend far beyond its body, likely used to detect food particles drifting in the water. Its common name is somewhat misleading. It doesn't feed on blood. Instead, it's a detritivore, using its sticky filaments to collect marine snow, sinking organic debris like fecal pellets and crustacean parts. When threatened, it exhibits a peculiar defense posture unlike any other cephalopod. Instead of fleeing or squirting ink, it has lost its ink sac. It draws its webbed arms up and over its body, inverting its cloak to cover itself. This exposes the underside of the cloak, which is lined with spiny projections called cirri, presenting a prickly appearance. It can also emit bioluminescent particles from its arm tips to confuse predators. This pineapple posture, combined with its dark color and large eyes, likely contributed to its infernal name. Deep-sea mining, unknown consequences. Beneath the waves, lying on or just below the deep ocean floor in vast quantities, are mineral resources that have begun to attract significant commercial interest. Polymetallic nodules rich in manganese, nickel, copper, and cobalt carpet some abyssal plains. Cobalt-rich crusts cover the slopes of seamounts, and massive sulfide deposits containing copper, zinc, gold, and silver form around hydrothermal vents. As land-based deposits become depleted or more difficult to access and demand for metals used in technologies like batteries and electronics grows, the prospect of mining these deep-sea resources is becoming increasingly viable, pushing humanity towards a new industrial frontier. However, this push for deep-sea mining is fraught with profound uncertainty and potentially devastating environmental consequences. The baffling aspect is our almost complete lack of understanding regarding the long-term ecological impacts of these activities. Deep-sea ecosystems are characterized by slow growth rates, long lifespans, high sensitivity to disturbance, and unique biodiversity, much of which remains undiscovered. Mining operations would involve scraping nodules off the seabed, grinding crusts off seamounts, or excavating massive sulfide deposits. This direct physical destruction would obliterate habitats and the organisms living within them over vast areas. Recovery, if it happens at all, could take centuries or even millennia due to the slow pace of life in the deep. Microplastics in the abyss. We often associate plastic pollution with surface waters, beaches, and marine life near the coast. However, one of the most shocking and sobering discoveries in recent oceanography has been the detection of microplastics, tiny plastic fragments less than 5 millimeters in size, in the most remote and seemingly pristine environments on Earth. The deep ocean trenches, including the Mariana Trench, the planet's deepest point. These findings demonstrate the pervasive and insidious nature of plastic pollution, confirming that our waste has managed to infiltrate virtually every corner of the marine environment, from the sunlit surface to the abyssal depths. How do these tiny plastic particles travel thousands of meters down to the ocean floor? The exact pathways are complex and still being fully unraveled, representing a significant mystery. Microplastics enter the ocean from numerous sources, including the breakdown of larger plastic debris, microbeads from cosmetics, fibers shed from synthetic clothing during washing, and industrial discharge. Once in the ocean, they can be transported by surface currents over long distances. Some particles may sink slowly on their own, but a significant portion likely reaches the deep sea by being incorporated into marine snow, the sinking aggregates of organic matter that form a key food source for deep-sea life. Animals consuming plastic particles at the surface can excrete them in fecal pellets, which sink rapidly. Microplastics can also attach to sinking biological debris. Ocean currents, including deep-sea currents and underwater canyons that funnel material downwards, likely play a role in concentrating plastics in certain deep-sea areas, including trenches. The 52 Hz whale, A Lonely Song. Amidst the cacophony of known underwater sounds, the clicks of dolphins, the songs of humpbacks, the calls of blue and fin whales, Navy hydrophone arrays tracking submarines during the Cold War began picking up something unique and perplexing starting in the late 1980s and early 1990s. It was a distinct whale call, but unlike any other recorded. Its key characteristic was its frequency. It called at around 52 Hz, significantly higher than the typical frequencies used by the largest baleen whales. Blue whales typically call between 10 to 40 Hz, and fin whales around 20 Hz. This unique acoustic signature led to its nickname, the 52 Hz whale. The calls were detected repeatedly over the years, particularly in the North Pacific, often following patterns of movement suggestive of a large whale's migration. However, the sound source was always solitary. It was never heard traveling with or interacting acoustically with other whales. Its call pattern also differed slightly from established whale songs. This led to widespread speculation and a touch of romantic melancholy. Was this a lone whale, perhaps the only one of its kind, calling out at a frequency that other whales couldn't understand or wouldn't respond to? The media often portrayed it as the world's loneliest whale, capturing public imagination. Milky Seas phenomenon. Imagine sailing across the ocean at night and finding yourself surrounded not by dark water, but by a vast, eerie, uniform, milky white glow stretching as far as the eye can see. This is the Milky Seas phenomenon, one of the most spectacular and rarest forms of large-scale marine bioluminescence, reported sporadically by mariners for centuries, but only scientifically documented relatively recently. Unlike the fleeting flashes or sparks of light commonly produced by individual organisms, Milky Seas involve immense areas of the ocean's surface, sometimes covering thousands of square kilometers, larger than the state of Connecticut, glowing continuously with a soft, steady, whitish light for hours or even days. The effect is described as otherworldly, like sailing over clouds or through snow. What causes these incredible large-scale luminous events? The leading hypothesis points towards massive blooms of bioluminescent bacteria, specifically Vibrio Harvey or related species, colonizing particles or possibly interacting with blooms of phytoplankton, like certain dinoflagellates in the surface water, under specific conditions perhaps triggered by nutrient availability or certain oceanographic factors. These bacteria multiply to astronomical numbers, potentially trillions upon trillions in a concentrated area. Through a process called quorum sensing, where bacteria communicate via chemical signals, they might coordinate their light production once their population density reaches a critical threshold, causing the entire water mass to glow simultaneously and persistently. The colossal squid beyond giant. While the giant squid, Architeuthis dux, often steals the limelight as the quintessential sea monster, another, arguably even more formidable cephalopod lurks in the frigid depths of the Southern Ocean. The colossal squid, Messonychoteuthis hamiltoni. Though potentially slightly shorter in total length than the longest giant squids due to relatively shorter tentacles, the colossal squid is believed to be the largest invertebrate on Earth by mass. It's a much bulkier, heavier animal, with estimates suggesting mature females could potentially weigh up to 500 kilograms, 1,100 pounds, or possibly more. Its body mantle is significantly wider and more muscular than that of the giant squid. What truly distinguishes the colossal squid besides its immense bulk are its fearsome arms and tentacles. While the giant squid has tentacles lined with simple suckers, the colossal squid possesses suckers equipped with sharp, swiveling hooks, some three-pointed, embedded within the sucker rings on its arms and the clubs at the end of its two longer tentacles. These rotating hooks would provide a devastating grip on prey, likely including large fish like Patagonian toothfish and possibly even other squid, preventing escape in the deep, dark waters around Antarctica where it primarily lives. It also possesses the largest beak of any squid, capable of shearing through flesh and bone. Like the giant squid, it has enormous eyes adapted for vision in near-total darkness. Deep-sea coral bleaching events. Coral reefs are typically associated with shallow, warm, sunlit tropical waters where symbiotic algae zooxanthellae living within the coral tissues provide them with energy through photosynthesis. Coral bleaching in these shallow reefs occurs when environmental stress, primarily elevated water temperatures, causes the corals to expel these vital algae, leaving their white calcium carbonate skeletons visible through their transparent tissues, hence bleaching. It was long assumed that deep-sea corals, which live in cold, dark waters far below the reach of sunlight and lack these symbiotic algae, would be immune to this type of bleaching. However, recent observations have revealed a startling and mysterious phenomenon. Deep-sea corals can also bleach, or more accurately, exhibit tissue loss and paling, suggesting they too are vulnerable to environmental stress. Since deep-sea corals don't rely on zooxanthellae, their bleaching must have different causes. Instead of expelling algae, these events seem to involve the corals losing tissue biomass, thinning or retracting their polyps, sometimes leading to partial or full mortality, exposing their underlying skeletons. What environmental stresses could be triggering these events in the stable, cold, dark conditions of the deep ocean? This is the central mystery. Researchers are exploring several potential culprits. Subtle but significant changes in deep water temperature, even minor increases, could stress these highly adapted, cold water organisms beyond their tolerance limits. Ocean acidification caused by the absorption of excess atmospheric carbon dioxide lowers the pH of seawater and makes it harder for corals to build their calcium carbonate skeletons, potentially weakening them and making them more susceptible to stress. Ghost ships of the deep. The deep ocean, particularly in certain basins with low oxygen levels and anoxic conditions, acts as an extraordinary preservation environment. The lack of oxygen combined with cold temperatures and darkness dramatically slows down the biological, chemical, and physical processes that typically degrade materials like wood, textiles, and even some metals in shallower waters. This has led to the astonishing discovery of ghost ships, ancient and historical shipwrecks resting on the deep seabed in remarkable states of preservation, looking almost as if they sank only recently, despite being centuries or even millennia old. Discoveries in areas like the Black Sea, where a deep anoxic layer prevents wood-boring organisms and minimizes decay, have been particularly stunning. Expeditions using advanced ROVs have revealed Roman, Byzantine, and Ottoman-era shipwrecks sitting upright on the seafloor with masts still standing, rigging partially intact, carvings visible on their timbers, and sometimes even their cargo undisturbed within the hulls. These incredibly preserved vessels offer unparalleled insights into shipbuilding techniques, maritime trade routes, and daily life aboard ships from past eras, providing details lost from historical records or less well-preserved, shallow water wrecks. Finding a 2,400-year-old Greek merchant ship almost perfectly preserved, as was found in the Black Sea, is like opening a time capsule from the ancient world. Eelpout fish live birth mystery. Reproductive strategies in the animal kingdom are incredibly diverse, shaped by the specific challenges and opportunities of different environments. In the deep sea, where conditions are stable but resources can be scarce and encounters between individuals infrequent, some species have evolved unusual methods to ensure reproductive success. Among the most peculiar are the reproductive strategies observed in some species of deep-sea eelpouts, families Zoacidae, bottom-dwelling fish found in cold waters worldwide, including the abyss. While many fish release vast numbers of eggs and sperm into the water, broadcast spawning, certain deep-sea eelpouts have evolved viviparity, giving birth to live young, which is relatively uncommon among bony fishes. What makes some deep-sea eelpout reproduction particularly baffling is the degree of parental investment and the nature of the offspring produced. Some species exhibit superfetation, simultaneously carrying multiple broods at different stages of development within the ovary. Even more remarkably, certain species give birth to only a very small number of young, sometimes just one or two, which are exceptionally large and highly developed at birth, essentially miniature versions of the adults. In some cases, the developing embryos within the mother receive nourishment not just from a yolk sac, but potentially through specialized structures, allowing nutrient transfer from the mother akin to a primitive placenta, matrotrophy, or by consuming unfertilized eggs or smaller siblings within the ovary, oophagy or adelphophagy. Giving birth to a single, large, well-developed offspring represents a massive energy investment by the female.